Hi guys, so now we're on chapter 2. So now this one kind of does a little bit of review, going back into chemistry, some physics, a little other pieces tied into that one. All right, so going in, again, you have your questions that you should be able to answer by the end of this. So as we move through, we're going to go through and start off into our matter versus mass. When we talk about matter, that's the amount of space that something has. So matter isn't defined. It's basically like if you have a box, how much can you fit in that box? That's your matter. So the matter of a single basketball is going to fill that box differently than a single ping pong ball. So that's when we start to look at the differences between. Then we go into the amount of mass that it has. The mass is going to tie, it's the amount of matter an object contains. So it's like, so if I handed you a basketball, yeah, you've got mass on the outside of it, but the inside of it is hollow. Versus if I hand you a bowling ball, different amount of mass. And it's why we use mass and volume in order to discuss density. And so if something's got more mass, it's going to, in a smaller volume area, aka in that space, it's going to be, you're going to feel it. It's going to feel more rough and tough. So kind of like my little eraser here. It's going to have a greater density because those molecules are packed tighter and closer to each other than my little cap here. The cap has got open space, open gaps. So it's got mass, so does this. They both take up space, so they have matter. But the difference is that this one is going to have some greater density. It's going to feel it. You can feel the parts that are there, okay? So that's kind of the difference between those. So then we start to talk about atoms. Why are atoms important in this? Well, we're all made of them. The earth is all made of them. The air around us is made of it. The water around us is made of it. Now, some atoms, when we put them together and they make molecules, those molecules are toxic. That's where we start to talk about the impact on the environment. If we have less of those molecules, aka water shortages, that's where understanding how those work and how those connect and how they function. So remember, you have your atom, okay? Around your atom, you have your protons, neutrons, and then on the inside, you have your electrons. And there's different elements on the periodic chart. Some are going to be ones that we can find everywhere, aka oxygen, hydrogen, carbon, nitrogen, okay? Those are going to be common ones that we're going to find everywhere, and carbon is in every single living life form like yourself. So whether it's a plant, whether it's a bacteria, whether it is a blue whale, everything is going to have that carbon piece in it. And so understanding that helps you understand where stuff starts to fit, okay? We're not going to memorize the periodic chart. You will need to be able to identify stuff on there. So when we get to our nuclear unit and looking at uranium, when we get to indoor air pollution, we're going to talk about radon. Like I said, for us, we are carbon-based organisms. When we talk about carbon, like in chapter 1, we talked about methane versus carbon dioxide. So that's where we're going to start to see where those molecules, those pieces are going to start to tie together, okay? Don't really need to worry about your atomic number or mass number. That's inconsequential. Isotopes going through, so if I tell you radon 222, radon 222 is going to be a typical one. But if we talk about the different levels of uranium is going to have different isotopes. And so depending on the isotope depends on the reactivity. So then we go into radioactivity. So we talk about radioactive decay. You've heard this with carbon dating in order to figure out how old a fossil is. Now understand, I know, news says and online you'll read that there are some, validity into those studies of how truthful it is about carbon dating and how reliable that source is. For us to try and figure out time frames, it's still in there, but nevertheless, radioactive decay does occur. So over time, things do break down. They do adjust, hence the phrase half-life. So half-life is the amount of time that it takes to cut in half. So for example, if something's got a half-life of 200 years and it starts off at 200 grams, so after 400 years, it's going to have 200 grams. So, or sorry, if it started off at 200 years, 200 grams. So at 400 years, we're at 100 grams. 600 years, we're at 50, and so forth. It keeps cutting in half as it moves along. AKA, if you look at a graph for that, you're going to see here's your y-axis, here's your high amount of grams at the top, whenever it was originally what it is. As time goes on, it starts cutting in half and cutting in half and cutting in half, and those mass values start getting less and less. So those numbers start to drop, okay? Now, we're going to be just talking about different types of bonding. Why is that important? Because then it tells you kind of how it might act in the environment. That's where that chemistry piece comes in. So let's go into different types of bonds. So we have covalent, ionic, and hydrogen. So going into your covalent bonds. Covalent bonds are typically your ones that you're going to find on your non-metal side. So that's why you see carbon and hydrogen on there. So you'll also see carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen, nitrogen. Carbon, hydrogen, oxygen, nitrogen, and phosphorus. Okay? Go back to your bio times. Cho, chon, chomp. And that's where we start to develop our macromolecules. So covalent bonds are really big in our macromolecules. That's what makes us. Okay? And so all of those macromolecules are the things that decide how we function, what we do, us as organic matter. So a lot of times you'll see that when we talks about organic or biotic. You need to start putting those pieces together as far as a link. Okay? So then we start to talk about ionic bonds. Okay? Ionic is going to be a metal and a non-metal. Sodium chloride is going to be one that you're familiar with. That's going to give you salt. So when we talk about salinity changes in the ocean, so if that's the case, because technically, if you remember back to chemistry, if I have salt, when it's in water, basically they'll pull the hydrogen and the oxygens because of its positive versus negative. So when we start to talk about the hydrogen end of water, it's going to pull on that negative chlorine. And we talk about the oxygen part on water is going to pull on that sodium, and they're going to dissociate. So as water evaporates, sodium and chlorine come back together. And if that's the case, then our salinity increases. And you end up with stuff like the Dead Sea, where you can float on it because there's so much salt in it. But there's very little life there. So then if there's very little life there, if our oceans are having issues and they're having increased salinity rates, guess what's going to happen to the life there? That's one of the things why we have to understand how those ionic bonds kick into place. Lastly, like I already said, hydrogen bonds. So when we talk about hydrogen bonds, we're going to have to talk about water, and we're talking about your genetics. Okay, so we talk about that polar end. That's going to be your water base. That polarity, that positive negative charge to it, is what's going to pull on that sodium and pull on those chlorines and work on that dissociation. Hydrogen bonds are the piece that keep your DNA sides of your DNA strand together. So DNA is a little important, especially as we talked about in that last one. In chapter 1, we talked about genetic diversity and how that impacts the health of an area. That if a species is genetically diverse, it's healthy. And if there's enough healthy species in that group, and the next group, and the next group, and the next group, you start to build a more diverse ecosystem. And it just begins to trickle down from there, that it does healthier and healthier, and stuff can function like it needs to. Okay, so like I said, there's your polarity of water. You can see on the screen where you have your hydrogen atoms. There's your positive. Then you go to your oxygen atom, and there's the negative. All right, and because of this, this is where they start to connect to each other. You can see it down here in the bottom. In other words, that water starts to create a connection. So when we talk about those connections, and we look at how water acts towards another, okay, it's going to be what we call cohesive, or have cohesive properties. That cohesion is what holds one water to the next. So if you had water on your finger, the reason why it forms that little droplet on your finger is going to be cohesion. And so the fact that the water is stuck to you is another property of water known as adhesion. And that adhesive property is what sticks to you, makes it stick in a lake, makes it stay where it needs to be, run through the middle of a tree, and do the job that it's meant to do, which is to help that tree live and exist. So understanding those properties of water is what makes a difference on how life functions. All right, and so we kind of talked about some of those, and then tying into surface tension. Surface tension is the reason why, for some of you, can float. The reason why a boat will stay on the water. If you set up a boat correctly, you create surface area to volume ratio that will apply to surface tension, and water pushes up and boat pushes down. Boat doesn't push down more than the water pushes up. Laws of physics. Okay? So we start to get those forces and the boat stays floating. Okay? So that surface tension is important when we talk about how it can function and be an insulator for us. So because of that high surface tension ties into the fact that water also has a high boiling point and a low freezing point, and so keeps water pretty stable, and which makes our world function well, because water is huge when it comes to the earth staying normal, functioning like it needs to, maintaining temperatures. Those are all the things that we start to see because of that setup, because of the large quantity of water that we see. Because remember, surface is more water than it is land. If it was converse to it, if the proportions were different, we would have been, we would have been too hot and wouldn't be able to function, especially with what we do, with what goes into our atmosphere. Not a good situation, okay? Going into acids and bases and pH. So remember, you have your pH scale. We kind of talked about this with the black water versus the clear water. And when we start to go 8 to 14, we're starting to go basic. All right? And that's where we have those OH ions. And then when we talk about acids are when we start to go through and talk about our 0 to about 6, almost 7. 7, remember, in the middle is your neutral. Now, remember, every time we move one spot to the next, this is a logarithmic piece. So that means it goes to a power of 10. So as I move from a 7 to a 6, it is 10 times stronger than a 7. If I go from a 7 to a 9, that's 100 times stronger. And that's one reason why you're like, but it's not that much. It's just, so when we talk about that little cup that we used in that lab that was clear with a pH of 7, when we went to the black water, which had a pH of 8, it's 10 times stronger, 10 times more OH ions, hydroxide ions, than the 7. So it's understanding that as we increase in severity. All right. This is part 1. We will continue with part 2 in a minute.